Okay, here we are, part two of my calculation of an electric field due to a charged disk. I did this already, but I'm going to do it again because I want to point out right here what I want to focus on, and that's that I want to show that my numerical calculation agrees with these expressions for the electric field due to disk. So here's the best expression for the electric field due to the disk, and then if you're really close, we could use this one, and if you're really, really close, you could use that one. I should point out that look, let's switch over to the Python. Okay, so here is my previous code that I'm going to just totally start over on. But I do want to, in case you missed it, link down below. I'll turn off this camera because no one really cares. I care, but so what was I going to say? Oh yeah, so this is I did not mention that this part right here, when I generated a 10,000 points to represent a disk, that would make this a Monte Carlo simulation. And some people are going to say, hey, it's a Monte Carlo. Yes, and I didn't say that, okay? But I know that it's a Monte Carlo simulation. So what I want to do though is make that graph. I don't want to make the visual anymore. So I'm going to throw away the visual stuff and I'm just going to focus on the graph, and that'll make it run faster and we can have as many data points as we want. So let's just go ahead and copy this code. Copy it. There. So now I have a new version right there. I'm going to keep K, I'm going to keep Q, I'm going to keep N. Let's put N as, start off as small. Now, what I want to do is to first make the points, which I've already done. And then I want to make a function to calculate the electric field at different locations. So that's what I really want to do, change this into a function. So the disk, don't need that. Just going to delete it. I don't want to make anything visual. That this stuff right here just generates the data points. I'm going to keep that as it is. This I do not need. I don't even need DR. I just need this. I don't need that. I need this stuff right here. I need how to calculate the electric field vector at a particular location. So let's go ahead and make a function. And I'm going to call it def E. I know that seems kind of weird, but that's true. And what parameters am I going to pass to that? And this is, you might be mad, okay? But I'm not going to pass the data points. I'm just going to use those as global. I'm just going to pass RO for observation location. That's all I'm going to put in there. Okay. So once I know that, I can say, I can copy all this stuff. And let's see, fix it. So that should be right there. Okay, let's see. I think this is okay for RQ in RQ. And this is, I'm going to change this. I don't have R. This is RO, right? The observation location. And everything else is good. And then that will put, then I'd say return E. So this function up here makes all the data points. And this function calculates the electric field at some observation location RO. So let's just check this out and see if it works. So I'm going to say let's just print, let's just do this. Print E at vector 0, 0, what did I use before? 0.03. I don't remember. Okay, let's run that. Let's call this something else. Comparison E due to disk. Now run it. I got an error. And that's because there is no variable called Vtor. So I should change that. There's no Vtor. Where did I do that? Vtor right here. Idiot. It's okay to call myself an idiot. Okay, there. I think that looks right because it's pointing in the Z direction. These values are small. Let's say they should be close to 0. If I increase this to 10,000 data points, then I get, they're still small. Let's do one more. I want them to be 0. I have made an error. I went too big. I flew too close to the sun. too many data points. Because see, if I increase this by a factor of 10, the number of data points, not only do I make more data points, but my calculation's much longer, right? Because now I have to go through more data points each time to calculate the electric field. It should work. I think it's going to finish. And that's why I was doing my delayed tactic. But I'm scared now, so arg. Let's just reload the whole page and change that to 0, and let's see if it runs again. Okay, note to self, don't do that again. Okay, so 10,000 is my limit. I think it's working. So what I want to do now is let's first make a plot of the exact electric field as a function of distance due to my analytical calculation, which I showed you at the beginning. So I'm going to go right here, and let's just say down here, I guess. Let's say t graph equals graph. And I should include a tutorial on graphing, if I remember. Title equals E due to disk. I like to put the title in there because it spaces it out correctly. X title is going to be equal to Z in meters. And Y title is going to be EZ, that's E sub Z, in units of electric field in volts per meter. Let's just do newtons per coulomb. It doesn't matter. Okay, that's that. Now I'm going to say FA equals G curve, color equals color.green. Let's start with green. And label equals analytical 1. So now what I want to do is start with my value, my location of my electric field, where I want to calculate the values. And I can just start with that at Z. I could go to Z equals 0, but I don't want to do that because when I make an actual numerical calculation, I could get myself into trouble because I could put my value on an actual random data point. Not highly likely, but it could happen. So let's say Z equals 0.005. DZ equals 0.005. Let's just try that. That seems like a lot. Okay, but that's fine. And now I'm going to say, oh, this will be easy. While Z is less than 0.05, I don't know, just picked a value. I need to calculate the electric field. So let's say EA1. This is the analytical version 1. It's going to be equal to, let's say, I need to go up here, get my equation sheets. I don't know if you know what you think, but I don't actually memorize this stuff. So I do need epsilon naught. So let's, the way I wrote that, I could do it 4 pi. Let's just do epsilon naught. So let's call this EPO. And so 1 over 4 pi epsilon naught equals 9 times 10 to the 9th. So epsilon naught, I don't know, let's see. 1 over 4 pi epsilon naught equals 9 times 10 to the 9th. So epsilon naught equals 1 over 4 times pi times 9 times 10 to the 9th. Is that right? Yep. So EPO equals, I'm just typing this out, 1 divided by 4 times pi times 9E9. Okay. So now go down here and calculate. It was, let's also calculate the area. A equals pi times r squared. So it's Q divided by 2 times A times epsilon naught. And then multiply that times 1 minus Z divided by r squared plus Z squared to the 3/2. To the 1/2. No, yeah, to the 1/2. So it's square root. Okay. Now let's plot that. So FA dot plot Z EA1, and then increase Z. Z equals Z plus DZ. Let's see if this runs. There's always a chance it won't. Run it. Check it out. It worked. Okay. So there's my electric field as a function of distance away. Everything's peachy keen. Is that a real word? Okay, now let's make another graph. So up here, another plot. So let's say Fn equals G curve. Not G, I thought that looked wrong. Color equals color.blue. Label equals label. Numerical. And then down here, I'm going to also plot. I already have that function, right? So I'm going to say, let's just plot it. Fn.plot z e. Oh, I need my. I can do it. E of vector 0, 0, z dot z. So here I need to give it a vector location, which I did right there. And then I can't plot the vector because this returns a whole vector. I only want the z component. I think that's going to work. Let's check it out. It's going to take longer. Okay. And you'll notice that you do get a deviation as you get really close, because now if I run this again, I think my deviation will be a little bit different, but far away they match up, I mean, almost identical. Let's run it again. See, now it's greater, because this is, you're going to get the random fluctuations because you're really close to some points and not so close to other points. So in fact, I should probably not even do that, but that's fine. I think I'm pretty happy. I mean, that's pretty amazing if you think about it. Now we're going to make the approximation if you're close. Okay, so let's go up here to FA2 equals G curve. Color equals color.red. Label equals analytical 2. Okay, that's FAN2. So the next one I'm going to calculate EA2 equals, and now I'm going to use my approximation formula of Q divided by 2 times A times EPO, epsilon naught, times, looking at my formula here, 1 minus Z divided by R. And let's plot that. FA2 dot plot Z EA2. Let's see how that adds up. So you'll notice up here in this region that all the solutions agree, but once you get further away, the analytical solution number 2 quickly diverges. I mean, it goes way out of whack. So let's just change this plotting, and let's go from, let's just go up to about here. This is x equals 0.02 centimeters. So let's say, let's change this to 2. There. Now they all they fairly agree. And you'll notice that the green and the red are exact calculations. Well, an approximation of an analytical calculation. If I run this again, that blue line may shift because it's Monte Carlo randomly generated. And see there, it shifted even again. Okay. Let's do this. Let's change this to 20,000. Right? I mean, that should do 20,000. Oh my gosh. Oh, I got scared. Okay, so there you go. Now we have one more calculation, and that is if you're super close. So let's say FA3 equals G curve, and let's just leave this as black. Curve, leave as black. Label equals analytical 3. Analytical 3. And then down here, I can calculate that. EA3 equals approximately Q divided by 2 times A times epsilon naught. And then I need to plot that. So FA3 dot plot ZEA3. Let's see what happens there. And you'll notice that it doesn't look anything like those because that's a constant value. I said it's a constant. So I need to get a lot closer in order for those to be true. And now I'm scared, but let's just do it anyway. So let's go from Z equals 0.01 Let's put DZ as 0.01. And let's go up to 1. Let's go up to 5. Let's go to 5. No, that's pretty. That's not too hard. Let's go to 1. No, 1. I'm scared. Because look, now there's 10 steps. And, oh, look at that, how close that is. So let's just go up to, let's get even closer. 0, 5, 0, and let's go to 0, 1. So you'll see here that the different analytical versions agree very. I don't even know what happened to the green one. I guess it didn't. It went crazy. I don't know where it is, unless it's right on top of that. These are very close together, and it's not too terrible, right? Let's run it again because that 9,000 is going to change. It's a random thing, so now it's below. So it's going to flip up and down, and I think it's okay. Am I still at 20,000? Let's go up to 30,000. Ooh, flew too high. It's going to run. Okay. So it crosses over, and we're in this really. That's not a really great approximation, right? But this one is the red one. And where did the green one go? Is it just right on top of that? Maybe it's right on top of that. Let's turn off. The red one is 2. So if I don't plot 2, do I see the green one? Yeah, so it was just on top of that. That's why you couldn't see it. Okay, so those agree, and I'm pretty happy with this. This is the one that I really want to use, but it agreed with the other two. And I'm going to do that for the electric field due to a capacitor, which I'll derive and then plot and do numerically all in one video, but I'll stop here because this is already 17 minutes. That's not so bad. Okay, so there you go. Monte Carlo. Remember, Monte Carlo, that was the key. Of course, I'll give you the code down below. Bye.